Welcome dear learners. We are continuing Unit 2 Chemical Bonding and Molecular Structure. In the present module, we are discussing VSEPR Theory. In this module, there is an introduction, postulates of VSEPR theory, geometry of molecules where central atom without lone pair of electrons, geometry of molecules where central atom with lone pair of electrons, VSEPR theory, its advantages and limitations, and problems based on these concepts. First of all, introduction. Lewis' concept is unable to explain the shape of molecules. You are familiar with the Lewis concept of covalent bond. It is unable to explain the shape or geometry of molecules. The VSEPR theory, that is valence shell electron pair repulsion theory, provides a simple procedure to predict the shape of covalent molecules. It should be noted that the covalent bonds are directional. Therefore, covalent molecules have a definite structure and geometry. And this theory, that is the VSEPR theory, is a theory that provides simple procedure to predict such a shape or geometry of covalent molecules. The VSEPR theory helps predict the shape or geometry of molecules and polyatomic ions based on repulsion between valence electron pairs around the central atom. That is, the ultimate focus of the valence shell electron pair repulsion theory or VSEPR theory is the repulsion between valence electron pairs around the central atom in a molecule or an ion. VSEPR theory was proposed by Sidgwick and Powell in the year 1940. This VSEPR theory is also called the Sidgwick-Powell theory. This VSEPR theory proposed in the year 1940 was further developed and redefined by Nyholm and Gillespie in the year 1957. That all about the historical aspect of the VSEPR theory. The theory assumes the electron pairs, that may be both bond pair and lone pair, arrange themselves in such a way to minimize repulsion, thereby determining the molecular geometry. That means the ultimate focus is electron repulsion. Electron pairs present in the valence shell may be of two types. The electron pairs present in a bond, that is called the bond pair. The electron pair that is not take part in chemical reaction or chemical bond, that is called the lone pair. The lone pair as well as bond pair present in the valence shell of the central atom offer some repulsion, mutual repulsion, and the VSEPR theory focuses on such repulsion, and the geometry should be in such a way that there should be minimum repulsion, thereby maximum stabilization. In a CH4 molecule, let us consider it as an example. In CH4 molecule, the central atom carbon has 4 bonding pairs and no lone pairs. You know, there are 4 valence electrons in the central atom carbon. These valence electrons are forming or paired with electrons of hydrogen to form 4 covalent bonds. So, there is no lone pair of electron in the central atom carbon, or simply you can say that all the electron pairs are bond pairs, and these 4 bond pairs are arranged in such a way of minimum repulsion to get a tetrahedral geometry. In a similar way, you can predict the geometry of several molecules with and without the lone pair of electrons around the central atom. This is one of the most important applications of the VSEPR theory. It is a simple theory which can be used to predict the geometry and shape of molecules or ions based on valence shell electron pairs present around the central atom The electron pairs may be lone pair or bond pair. This is the CH4 molecule in its tetrahedral shape. The bond angle in CH4 molecule is 109 degree 28 minute or can be rounded off to 109.5 degree. The central atom carbon is covalently bonded to 4 hydrogen atoms and the 4 CH bonds are arranged at the 4 corners of a regular tetrahedron with the bond angle nearly equal to 109.5 degree. Now we are discussing the postulates of valence shell electron pair repulsion theory. You have to keep the core concept that the VSEPR theory give emphasis to repulsion between electron pairs, that may be lone pair or bond pair, present in the valence shell of the central atom. And now we can have various postulates of the VSEPR theory. The main postulates of VSEPR theory can be discussed as follows. The first one, the shape of a molecule depends on number of valence shell electron pairs. The valence shell electron pairs may be bonded pair or bond pair or non-bonded pair. Non-bonded pair is otherwise called the lone pair, which are present in and around the central atom. These are some molecules with which we can illustrate the VSEPR theory. This is first molecule, that is nothing but methane. Here you can see only 4 bond pairs. These 4 bond pairs are situated at an angle of 109.5 degree. The second molecule is ammonia. The central atom, which is shown in blue colored ball, is the nitrogen. 3 hydrogen atoms are also seen there, and in ammonia molecule you can see the presence of a lone pair of electron. So there are 4 electron pairs, out of which 3 are bond pairs and 1 is a lone pair. And excluding that lone pair, you will get the shape of ammonia molecule, that is pyramidal shape. Whenever you are specifying the geometry, you have to consider all electron pairs. So including the lone pair, you can say that the geometry of ammonia molecule is tetrahedral with one position occupied by lone pair. If you are excluding lone pair, you will get the shape. So the shape of ammonia molecule is pyramidal. And because of the electron pair repulsion between lone pair as well as bond pair, the bond angle diminished it to 107 degree in the case of ammonia. And the last example is nothing but water. There you can see 2 lone pairs and 2 bond pairs present on the central atom, which is the red colored ball, that is the oxygen. In the case of water molecule, there may be repulsion between lone pairs, repulsion between lone pair and bond pair, and there is also repulsion between 2 bond pairs. All these repulsions lead to a net shape of water molecule. That shape is called bend shape. So the geometry is again tetrahedral with the 2 positions occupied by lone pair. Whenever you are mentioning the geometry, you have to consider both the lone pair as well as bond pairs. So ammonia, water and CH4 all have the same tetrahedral geometry. In methane, there is no lone pair. In ammonia, there is 1 lone pair, and in water, there are 2 lone pairs. So if you are excluding the lone pair, you will get the shape. In the case of methane molecule, there is no lone pair to exclude. So it is having similar geometry and shape. In the case of ammonia, the shape is pyramidal, but the geometry is tetrahedral with 1 lone pair. In the case of water molecule, the shape is bent, but the geometry is tetrahedral with the 2 lone pair of electron. So a molecule can have a fixed shape or geometry based on the interelectronic repulsion between various electron pairs, namely the lone pair and bond pair present around the central atom. Now we are entering into the second postulate of the valence shell electron pair repulsion theory. Pairs of electrons in the valence shell repel one another since their electron clouds are negatively charged. This is the third postulate of the VSEPR theory. The pairs of electrons tends to occupy such positions in space that minimize repulsion and thus maximize distance between them. The electron pairs, both bond pairs and lone pairs, are arranged in such a way that the repulsion between them is minimum. If minimum repulsion, there will be maximum stability and more stable will be the shape or geometry of the molecule. This represents the arrangement of two pairs of electrons, two bond pairs at different angles. In the first situation, the angle between two electron pairs are marked as blue line, and the angle between the electron pairs is 90 degree. In the second case, the angle is increased to 120 degree, and in the final arrangement, the angle between two electron pairs is taken as 180 degree. It is very well clear that in the last arrangement, the two electron pairs are separated at an angle of 180 degree. That leads to minimum repulsion and maximum stability. So, among these three arrangements, the more stable situation is the last arrangement, and the bond angle is the stable bond angle, and that is equal to 180 degree. We are now discussing the fourth postulate of the VSEPR theory. The valence shell of an atom, of the central atom in a molecule, is taken as a sphere with electron pairs localizing on the spherical surface at maximum distance from one another. This is next postulate, that is the fifth postulate. A multiple bond is treated as if it is a single electron pair, and the two or three electron pairs of a multiple bond are treated as a single super pair. This is an assumption that we are using in VSEPR theory. Now, the sixth postulate of the valence shell electron pair repulsion theory. Where two or more resonance structures can represent a molecule, the VSEPR theory model is applicable to any such structure. So, you are familiar with the concept of resonance. What do you mean by the term resonance? It is a situation where the structure of a molecule cannot be represented by a single structure, but more than one structure is required. That situation is termed as resonance. So, this postulate correlate VSEPR model with resonance structures. Now, we are discussing repulsive interaction between electron pairs. It should be noted that the repulsion is the core theme of the VSEPR theory. Repulsion between valence shell electron pairs is the core theme of the VSEPR theory. The repulsive interaction of electron pairs decreases in the order lone pair greater than, lone pair greater than, bond pair. Or we can say that the repulsion between two lone pairs is maximum and that between two bond pairs is minimum. So, you can simply say like this: LP repulsion greater than, LP repulsion greater than, BP repulsion, where LP represents a lone pair and BP represents the bond pair of electrons. So, the highest magnitude repulsion is from repulsion between two lone pairs, and the lowest magnitude is the repulsion between two bond pairs. While lone pairs are localized on the central atom, each bond pair is shared between two atoms. Localized electrons, lone pairs depicts localized electrons, and this bond pair represents shared electrons. As a result, lone pair of electrons in a molecule occupy more space as compared to the bond pair. This results in greater repulsion between lone pairs of electron as compared to the lone pair bond pair as well as bond pair repulsion. So, you have to keep this point in your mind. The highest magnitude repulsion is between two lone pairs, that is LP greater than, LP greater than, BP, where BP stands for bond pair and LP stands for lone pair of electrons. We have LP greater than, LP greater than, BP. We can arrive at some important consequence of this magnitude. This can be illustrated by taking water molecule as an example. I already mentioned the fact that in water molecule, the central atom oxygen has 4 electron pairs, out of which 2 are lone pairs and 2 are bond pairs. And the geometry of the water molecule is tetrahedral geometry with the 2 positions occupied by lone pair of electron. For a normal tetrahedral arrangement, we are anticipating the bond angle 109 degree 28 minute or 109.5 degree. But here in the case of the water molecule, you can see the bond angle between two OH bond is reduced to 104 degree 27 minute or nearly 104.5 degree. You know 60 minutes equal to 1 degree. So 27 minutes nearly equal to 0.5 degree. What is the reason behind the diminishing of the bond angle from 109.5 degree to 104.5 degree or 104 degree 27 minute? The decrease in bond angle can be related to the magnitude of the electron pair repulsion. We are knowing the fact that LP-LP repulsion is greater than LP-BP, which is again greater than BP-BP. So, minimal magnitude repulsion is BP-BP. So, in order to reduce the magnitude of the repulsion between two lone pairs, the bond pairs will come close together. As a result, the bond angle reduces to 104 degree 27 minute. So, this bond angle, this bend structure is a direct consequence of the postulate of the valence shell electron pair repulsion theory. Now, we are discussing the geometry of molecules. It is possible to predict the geometry of the molecules based on electron pairs, lone pair or bond pair, present around the central atom of a molecule or ion. First of all, we are discussing the geometry of molecules where the central atom without lone pair of electrons, that is, the central atom having bond pairs only, or all the electron pairs are bond pairs. We can discuss the geometry of such molecules. For the prediction of geometrical shapes of molecules with the help of VSEPR theory, it is convenient to divide molecules into two categories. The first category is discussing here, that is nothing but molecules in which the central atom has no lone pair. The second category is the molecule in which the central atom has lone pair of electrons and bond pair of electrons. That is, the central atom may have one or more lone pairs also. The geometry of molecules where the central atom without lone pair. We are giving more emphasis to this part now, and after this discussion we can move on to the systems where lone pairs are present on the central atom. First, we can focus on central atom without lone pairs. Let us fix capital A as the central atom and B as the bond pair to illustrate the geometry based on VSEPR theory. This is a common convention where A is the central atom, B represents the lone pair. Now, let us take the case of the first category of molecule, that is nothing but AB2 molecule. We are taking AB2 molecule. The number of electron pair here is equal to 2. Geometry of the molecule is linear because there is a central atom and two bond pairs are there. It is more convenient to express these two bond pairs at maximum separation of 180 degree. That leads to a linear geometry of the molecule as shown here. Here A is the central atom and two bond pairs are also, you can see here, and the bond angle between them is equal to 180 degree and the resultant shape or geometry is linear. The bond angle, as I mentioned, it is 180 degree, and a typical example is beryllium chloride molecule. This is the illustration of the beryllium chloride structure. The red colored ball represents the central atom beryllium and two white balls represents the chlorine atoms. This molecule has a linear shape with a bond angle of 180 degree. This is the more stable arrangement of a system with the one central atom and two bond pairs. Now we are considering another category, that is AB3 molecule where number of electron pairs is equal to 3, all are bond pairs, A is the central atom. Since AB3 is the molecular formula, you can see that there are 3 bond pairs and the geometry of the molecule, more stable geometry as per the VSEPR theory, is trigonal planar geometry, and this is the representation of the trigonal planar geometry. You can see the central atom A at the middle position, and bond pairs are around the three corners of a triangle. That's the name trigonal planar arrangement. The bond angle is equal to 120 degree, and the typical example is BF3 molecule. This is the arrangement of the BF3 molecule. A boron atom is at the central, and the three fluorine atoms are separated by 120 degree apart. Moving on to another category of molecule without a lone pair on the central atom, that is nothing but AB4 molecule. The number of electron pairs is equal to 4 since there are 4 bond pairs. The preferred geometry based on VSEPR theory is the tetrahedral geometry, and this is the tetrahedral geometry. A atom is at the center, B are at the corners, B represents the bond pairs, and the bond angle is 109 degree 28 minute in sharp value, and you can round off to be 109.5 degree. And the typical example is the methane molecule. The methane molecule with the bond angle 109.5 degrees is shown here, and the tetrahedral arrangement is very clear from the illustration. Now we are considering AB5 molecule. In AB5 molecule, it is clear that there are 5 electron pairs, all are bond pairs. The preferred geometry for such an arrangement is trigonal bipyramidal geometry, and this is the trigonal bipyramidal geometry. There is a triangle, one bond pair is above the position and other one is below the triangle. Such an arrangement is called the trigonal bipyramidal geometry, and here there are 2 bond angles. The in-plane bond angle, that is the bond angle in the triangle arrangement, is 120, and another angle is 90 degree. The typical example for this molecule is shown here. It is nothing but PCl5 molecule. Here there are 2 bond angles, and the illustration is also here. The red colored ball represents the central atom phosphorus, and the green colored balls represents the chlorine atoms. That is the trigonal bipyramidal geometry. Now we are entering into AB6 molecule. Here, as the molecular formula suggests, there are 6 electron pairs, all are bond pairs of electrons, and the geometry of the molecule is octahedral, and this octahedron is a regular arrangement with a bond angle of 90 degree, and S of 6 is a typical example for such a molecule that exhibit octahedral geometry and octahedral shape. Here geometry and shape are same because there is no lone pair around the central atom. This is the octahedral arrangement of S of 6 molecule. Now we are discussing the last category of molecule without lone pair on the central atom. This is AB7 molecule. The number of electron pair is equal to 7. This category of molecules are very rare, and the geometry of such a molecule is pentagonal bipyramidal with 2 kind of bond angles, 90 degree as well as 72 degree. A typical example and one and only stable such example is IF7. Here you can see a pentagon which is in plane. One fluorine is arranged above the plane, other fluorine is arranged below the plane. The in plane bond angle is 72 degree and the out of plane bond angle is 90 degree. This about the geometry of the molecules with only bond pairs around the central atom, that is the system without lone pair around the we are discussing geometry of molecules where the central atom with lone pair of electron in addition to bond pairs. Geometry of molecules where central atom with lone pair of electrons. In order to illustrate the concept, we are now fixing A as the central atom, B as the bond pair, and capital E as the lone pair. First of all, we are discussing AB2E molecule. From the molecular formula, it is very well clear that number of bond pair is equal to 2 since B is 2, number of lone pair is equal to 1 since E is equal to 1, and A is the central atom. The geometry of such a molecule is trigonal planar. This is because there are total 3 electron pairs around the central atom. That is why the molecule prefers a geometry trigonal planar geometry. This is the trigonal planar geometry. You can see the presence of one lone pair around the central atom along with the 2 bond pairs. In order to represent the shape of the molecule, you have to ignore the contribution from the lone pair. If you are removing the lone pair, you will get the shape. The shape of the molecule is bent. A typical example for this category AB2E type is SO2 molecule. This is the structure and shape of SO2 molecule. Now another category is AB2E molecule, AB3E molecule. In AB3E, number of bond pairs equal to 3, number of lone pair is equal to 1. There are total 4 electron pairs. So the molecule has a geometry of tetrahedral arrangement or tetrahedral geometry. This is the tetrahedral geometry. You can see the presence of a lone pair which is occupied at one corner of a regular tetrahedron, and we are mentioning the shape by ignoring the contribution from the lone pair. So if you are removing the contribution or if you are removing the lone pair, you will get the shape. The shape is trigonal pyramidal. A typical example of this shaped molecule with this type of molecular formula AB3 is ammonia. Here in the nitrogen atom there is a lone pair, and around the nitrogen atom there are 3 bond pairs. If you are ignoring the contribution from the lone pair, you will get the pyramidal shape of ammonia molecule. Now another category we are discussing is AB2E2 molecule. Here there are 2E and 2B. That means there are 2 bond pairs and 2 lone pairs. There are a total of 4 electron pairs, and hence the geometry is constant, that is tetrahedral geometry. And this is the tetrahedral geometry. If you are excluding the lone pair, you will get a bend shape to the molecule. Typical example is water molecule. In water molecule, the central atom has 2 bond pairs and 2 lone pairs. If you ignore the lone pair, you will get a bend shape for water molecule. Now, another category of molecule with the lone pair of electron on the central atom is AB4E. Here there are a total of 4 electron pairs, 1 lone pair and 4 bond pair. So 5 electron pair can take a fixed geometry of trigonal bipyramidal geometry. In the trigonal bipyramidal geometry, you can see the presence of a lone pair. That lone pair is arranged in a stable way in the triangle, and the shape of the molecule is seesaw if you are excluding the lone pair present in the triangle. So the shape of the molecule is seesaw shape. Typical example is SF4. Sulfur tetrafluoride is a molecule that exhibits seesaw shaped molecule. It is a molecule where the central atom sulfur has 4 bond pairs and 1 lone pair. Now we are discussing another category of molecule with the lone pair of electron, that is AB3E2 molecule. In AB3E2 molecule, there is a total of 5 electron pairs, out of which 3 are bond pairs, 2 are lone pairs, and since there are 5 electron pairs, the geometry of the molecule is trigonal bipyramidal, and the position of the lone pair of electrons, 2 lone pairs, are again in the trigonal arrangement, in the triangle, and the shape of the molecule, if you are removing that 2 lone pairs, then you will get a shape. The shape of the molecule is a T shape. And the typical example for such a system is ClF3. Here in ClF3 there are 3 bond pairs and 2 lone pair of electrons around the central atom chlorine, and the arrangement is here. If the lone pairs are ignored, you will get a T shape for the ClF3 molecule. Another category of molecule we are discussing is AB5E. Here there is a total of 6 electron pairs, 5 are bond pairs and 1 lone pair. Since there are 6 electron pairs, the molecule prefers an octahedral geometry. In the octahedral arrangement, you can see the presence of a lone pair at one corner of the octahedron, and if you are neglecting that lone pair, you will get a shape that is the square pyramidal shape. Typical example for such a category of molecule is BRF5. So BRF5 is a molecule which is having square pyramidal shape and octahedral geometry with one position occupied by lone pair of electron. Moving on to another category of molecule, that is AB4E2 molecule. Here there is the presence of 6 electron pairs around the central atom A, out of which 4 are bond pairs, 2 are lone pairs, and the preferred geometry is octahedral with 2 lone pairs. And if you are neglecting the lone pair, you will get a square planar arrangement. The typical example for such a molecule is XCF4 or xenon tetrafluoride. If you neglect the lone pairs shown in this picture, you will get a square planar shape to XCF4 molecule. Now we are discussing advantages and disadvantages or limitations of the VSEPR theory. Now we are focusing on advantages first, followed by disadvantages. The VSEPR theory is able to predict the geometry of a large number of molecules, especially the compounds of p-block elements accurately. It is also quite successful in determining the geometry of quite accurately even when energy difference between possible structure is very small. VSEPR theory is a useful model for predicting molecular shapes. Now, these are the disadvantages. The theoretical basis of the VSEPR theory regarding the effects of electron pair repulsion on molecular shapes is not clear and continues to be a subject of doubt and discussion. It does not explain everything about molecular geometry. For a more accurate understanding, hybridization, which is based on valence bond theory, and molecular orbital theory must also be considered. So, VSEPR theory is not a standalone theory. Now, we are discussing some problems based on the concept we have discussed. Some MCQs are here. This is the first problem. Which of the following statements about lone pair is true? These are the options. Lone pairs repel bond pairs more strongly than bonding pairs repel each other. Lone pairs do not affect molecular geometry. Lone pairs always increase bond angles. Lone pairs are always found in linear molecules. This is your option, option A. Lone pairs repel bonding pairs more strongly than bonding pairs repel each other. Now, another MCQ. The molecular shape of SF4 according to VSEPR theory. This is a direct problem. These are the four options: tetrahedral, seesaw, trigonal, bipyramidal and octahedral. It is very well clear that the shape of SF4 molecule is a seesaw. Now, we are looking on to another multiple choice question. The molecular shape of BRF5 according to VSEPR theory is trigonal, planar, pyramidal, T-shaped molecule, tetrahedral, and the question is about BRF3, which is structure analogous to ClF3, and it is clear that ClF3 or BRF3 both are molecules having T shape. So, your answer is option C, T shape. Which of the following statements about XeF2 is correct? These are the options in front of you. It has a bend shape, it is trigonal, pyramidal, it is linear, it has a tetrahedral shape. Absolutely, we can arrive at the conclusion that XeF2 is a molecule where the central atom has 3 lone pairs and 2 bond pairs. So, the molecule is definitely linear molecule, trigonal bipyramidal geometry with the 3 lone pairs, and the shape of the molecule is linear. Moving on to another MCQ. Why does PH3 have a bond angle smaller than NH3? These are the options. PH3 has a different hybridization. Lone pairs in PH3 experience weaker repulsion than in ammonia or NH3. Phosphorus has a higher electronegativity than nitrogen. PH3 has a tetrahedral shape. On arriving at the final answer, you can select option B as your answer. Option B, lone pairs in PH3 experience weaker repulsion than in ammonia. Now, this about the last MCQ of this module. The shape of IF7 molecule is. These are the options: pyramidal, octahedral, pentagonal, planar and pentagonal bipyramidal. It is very well clear that IF7 molecule is a molecule with 7 bond pairs around the central atom. It prefers pentagonal bipyramidal geometry as well as pentagonal bipyramidal shape. So, your answer is option D, pentagonal bipyramidal. That all about the present discussion. Have a nice learning experience. Thank you.